Hi everyone, my project is an automatic Bokehrama. So what is a Bokehrama? It comes from two words, bokeh and panorama. So we know that bokeh generally has a very narrow field of view. So to get this pleasing effect where there is a very shallow depth of field, we have to focus on the subject and we don't have much of the background. So Bokehrama tries to encounter that with this very pleasing effect, which gives the effect of using a very expensive medium format lens. To simulate this, we have to take a bunch of images using some zoom lens, and then we stitch them together using some software. This is a very manual process requiring a lot of manual intervention. Now, the problem statement is that given a set of images captured with a large focal length and a shallow depth of field, which we are doing, can we combine them automatically to create the desired Bokehrama? So these are some example captures that you can see here in the GIF. So the challenges associated with this is that one is creating this image matching graph automatically. And the second thing is that most of the stitching algorithms work with the distant objects or scenes. So they don't generalize well to when the object is very close to the camera, which is the case for us. Now, the proposed method, which is the automatic Bokehrama pipeline, it has this 5 major steps. So first we extract the features from the image. Then we do k nearest neighbor search. Then we use these neighbors and use some heuristics to remove the redundant edges, and we get a complete image graph about how these images are oriented, kind of like a jigsaw puzzle. And then we stitch the images and then we blend the images to remove the seams. So first, coming to the feature extraction step, I used SIFT for the feature extraction because you can see compared to FAST and or the other popular feature extractors, we have a lot of relevant features on the edges of the buildings, while FAST gives us a lot of redundant features throughout the building. Now, once we get the features, we will perform a matching with a KD tree to get the five nearest neighbors. Now, once we have the 5 nearest neighbors, we'll have a lot of redundant edge because each image is currently matched to 5 images, which have the highest number of features that match with it. Now, we'll use some heuristics to remove some of these edges. First, we will put some constraints on the homography matrix itself such that the images don't get skewed or flipped. Second, we'll impose some constraints on the edges from one image to another in terms of the number of features that it's matching to. So we'll eliminate some cyclical connections by following the edge that has more feature matches. Now, once we have done that, we will get this graph that has been created in an automatic manner, and we will feed this graph to an image stitching algorithm. In this case, we are using natural image stitching with global similarity prior because it has this its objective function has this 3 terms, the alignment term, which tries to keep the initial alignment intact without distorting the candidate images too much. This local similarity term, which is basically a regularization term, and this global similarity term, which prevents the parts of the images that are away from the overlapping region, in the non-overlapping region, to not distort too much. Okay, so this is a grid-based method, which is very robust and can generalize well to a lot of images. But this does result in some visible seams, as you can see here. So we end up using linear blending to get rid of those seams and get a perfect image. Now, so far, I have been showing all these results on this Times Square scene, which is very complicated, has around 21 images, but we can see how well this algorithm performs. Now, one caveat of this algorithm is that all this image matching that has been done, like which image is next to which image, that image matching graph, that has been done manually. So they get this result, and we can see that the buildings are kind of bent when they use their own manually annotated graph. Versus when we use the graph that comes from the algorithm that I just described using the heuristics, we do end up bending the lower part of the image more, but the buildings, which are the main subject, they remain undistorted. This is just a comparison between AP and which is as perspective as possible, and some other image stitching algorithms, which describes why I chose this particular method for the image stitching part. Okay, so now we have all the moving parts, and now we can move to the results of our captured images. So to demonstrate the effectiveness of this approach, I have compared it against an open source software, Hugen. So this is a image stitching software. Now we can see that when I run it on the images that I've captured, due to the translation of the camera, we get this blurred effect. Okay, but our result, though it also has some ghosting artifacts, it's a much pleasing and better result. And you can see this is the image that had been captured, a single capture, and look at the a large field of view have compared to this one. This just describes some of the matches that were there. Okay, this is another result which also compares the result that I obtained with, of course, from the Hugen software. And also OpenCV has its own native stitching algorithm, and we can see how it has bent the shelf in the background. Though, again, we do have some bending in the air conditioner and in the window behind and in the books in front, but still, compared to this results, this looks a bit more pleasing. Now, there are, of course, limitations to this method. Like we saw, there will be distortion artifacts because the object is so close, close to the camera. And image matching does get more complicated as we significantly increase the number of images. Now, so these are the references that I have used. And I would like to thank Professor Yanis for designing this amazing course and Tanli for helping during all the office hours. Thank you.